welcome to all. I'm Dr. Annam Renita, Department of Chemical Engineering, School of Biochemical Engineering from Satyabama Institute of Science and Technology. I'm going to give a brief introduction to engineering. All industrial processes involve unit operations and unit process for the conversion of raw material to products. Mostly an economical way is selected without any compromise in the quality. So in this aspect, unit process, you can say all reactions, say for example, oxidation, conversion, etc. play a key role. Some of the classification of reactions are homogeneous reactions, heterogeneous reactions, catalytic reactions, non-catalytic reactions, elementary reactions, non-elementary reactions. So let us consider A to be the reactant and B to be the product. So if A and B are in the same phase, say for example, if both of them are in the liquid phase or a gas phase or a solid phase, it is known as a homogeneous reaction. If any of one of them are in a different phase, it is known as an heterogeneous reaction. The catalyst is used for the process, it is known as catalytic reaction. If no catalyst is required, then it becomes a non-catalytic reaction. Elementary reactions are those which have a correspondence between the stoichiometric equation and the rate equation. So this is a stoichiometric equation and this is the rate equation. So if there is no correspondence between the stoichiometric equation and the rate equation, then it becomes a non-elementary reaction. Another term is known as molecularity. It's the number of molecules taking part in the reaction. If one molecule is going to take part in the reaction, it becomes unimolecular type of reaction. Two moles are going to take part in the reaction, it's a bimolecular reaction. And if three molecules are going to take part in the reaction, it's trimolecular reaction, and so on. So it's a theoretical quantity, it should be a whole number. So the rate of reaction can be defined as the amount of reactant disappearing per unit volume per unit time. And when we consider A giving product, the rate equation can be represented as minus RA is equal to minus 1 by V dNA by dt. This minus sign represents the disappearance of the reactant. So the reactant has to disappear to give the product. So there are various forms of the rate equation based on which term is important. Say for example, it's the volume of the reacting fluid, it becomes V into Ri. It's the weight of the catalyst, it becomes W into Ri dash. For the surface area, it becomes S into Ri double dash. And if it's the volume of the solid, it becomes AS Ri triple dash. And if it's volume of the liquid, it becomes Ri 4 dashes. So we have seen that the original rate equation is minus RA is equal to minus 1 by V dNA by dt. It can be modified based on a constant volume reaction or a variable volume reaction. So if it's a constant volume reaction, then dNA by V can be clubbed to be dCA. So this original rate equation gets modified to minus RA is equal to minus dCA by dt, which we take then to be the concentration dependent term of the rate equation. So this can also be written as minus RA is equal to rate constant K into the concentration of the reactant. So the order of the reaction is defined as sum of the parts to which the concentration terms are raised. So when we consider the reaction A giving P, we can write the rate equation to be minus RA is equal to K into Ca. So here if you see the sum of the power of Ca is just 1. Actually, since it's a one reactant, we can't tell it to be a sum of the power, but since we can just consider only the power of the reactant. When it becomes 2A giving P, here also since the reactant is 1, the number of molecules is 2. Here you can take the power of the reactant alone, a single reactant. And if it's like 2 reactants, we write the rate equation, like consider this equation, 2A plus 3B giving P. So the rate equation can be written to be minus RA is equal to KCA to the power of 2, CB to the power of 3. Here the sum of the powers can be taken, which is 2 plus 3 giving 5. So order of reaction is an experimental quantity. It can also be a fraction. So the rate of a reaction depends on the concentration as well as the temperature. So basically there are three theories which propose the dependence of rate on temperature. Arrhenius theory, transition state theory, and collision theory. So as per Arrhenius theory, the reactants, they need to possess a certain minimum amount of energy known as the threshold energy to become the products. So the equation is proposed to be K is equal to K naught e power minus E by RT. K naught is equal to P exponential factor and it has got the units of rate constant. And E is activation energy which can be written in terms of joule per mole or calories per mole. If two different temperatures are taken into account, then the equation can be modified as ln of R2 by R1 is equal to minus E by R 1 by T2 minus T 1 by T1 or ln of R2 by R1 is equal to E by R 1 by T1 minus 1 by T. Transition state theory proposes that the reactant molecules they will get converted into intermediate product and which transitions into the products. Now this intermediate product is highly unstable. And the equation proposed for transition state theory is K is equal to K naught T into E power minus E by RT. Collision theory states that reactant molecules have to collide with one another to become the products. And the equation proposed is K is equal to K naught T to the power of E power minus E by RT. As we have seen that order of the reaction can be found by experiments. Two different methods are utilized to find out the order. One is the integral method and the other is the differential method. So as per the integral method of analysis, it always puts a particular rate equation to the test by integrating and comparing predicate C versus T curve with the experimental C versus T data. If the fit is unsatisfactory, another rate equation is guessed and tested. Say for example, if we consider first order equation, then we have to plot that y is equal to mx plus c rate equation like minus 1 of 1 minus xa is equal to kt. That minus 1 of 1 minus xa will be the plotted in the y-axis and t in the x-axis. A straight line will be obtained which passes through the origin and the slope will give k. If it is not so, then whatever order that we have assumed, that is we have assumed the first order, it is not so. So we have to neglect that and we have to assume the next order. So it's like a trial and error method. Next is the differential method to find the order of the reaction. Differential method of analysis deals with the differential rate equation to be tested, evaluating all terms in the equation, including the derivative, dci by dt, and testing the goodness of fit of the equation with the experiment. So first we have to plot the CA versus T data, and then we'll have to draw a smooth curve to represent this data. So the curve most likely will not pass through all the experimental points. So then we'll have to determine the slope of this curve at suitably selected concentration values. So the slope will give dCA by dt which is equal to Ra. That is dy by dx, that's the slope. It's nothing but the rate of the reactions. So are the rates of reactions at these compositions. And then we can test a general, or you can say an nth order equation, which is minus Ra is equal to Kca to the power of n. Take the logarithm on both the sides. And then this also will be in the form of a y is equal to mx plus c. We can take log of minus Ra in the y-axis and plot of Ca in the x-axis. And we get a straight line, which the slope will give n, this will give k. Let's consider zero order reaction. So photochemical reaction is a classical example of zero order reaction. So as per zero order reaction, the rate of the reaction is independent of the concentration of the materials. So this is how the final equation is derived. So minus Ra is equal to minus dCA by dt is equal to Kca to the power of 0. So we can neglect that. So minus dCA by dt is equal to K. So take d2 to the other side. The limits for time and time t is equal to 0, it becomes Ca naught for concentration. Time t is equal to K plus Ca. So when we integrate and substitute the limits, the equation will become Ca naught minus Ca is equal to Kt. So this equation can also be represented in terms of conversion. Can be represented as Ca naught Xa is equal to Kt. Then finally, we need to draw a graph to validate the genuinity of the order. Next is the first order. So the first order equation is derived thus: minus RA is equal to CCA by dt is equal to KCA. So the constellation terms can group together. It becomes minus dCA by CA is equal to kdt. And substitute the limits, which are CA concentration CA naught at time t is equal to 0 and into CA at time t. So substituting the limits and integration of 1 by CA to give minus 1 of CA and integration of dt to give t. So we just have to substitute the limits, concentration CA naught to CA for time 0 to t. So this becomes minus 1 of CA by CA naught is equal to kT. In terms of conversion, this can be written as this minus dCA by dt can be written as CA naught dXA by dt, and CA can be written to be CA naught into 1 minus XA. So CA naught will get cancelled with the XA terms. So this becomes dXA by 1 minus XA is equal to K into take dt to the other side dt. So when time t is equal to 0, naturally there will be no conversion. So it becomes 0. Time t is equal to t, conversion is XA. So final equation is minus 1 of 1 minus XA is equal to kT, which has to be represented as a graph. So in terms of concentration, it becomes minus 1 of CA by C naught, this is time. It will give a straight line passing through the origin and the slope will be K. In terms of conversion, it becomes minus 1 of 1 minus XA, this is time. It will give also a straight line passing through the origin with the slope K. So there are variable volume reactions also. Say for example, popping of popcorn. So we can see that for the reaction, the popcorn size is very small, but after the reaction, it is large. So in that case, we have to account fractional change in the volume. So an important term known as epsilon is being introduced in terms of variable volume reactions. So the formula for that goes as volume at final conversion minus volume at initial conversion divided by the volume at initial conversion. So XA is equal to 1 means it's a final complete conversion. And XA is equal to 0 means the initial conditions of the conversion. And even the formula for volume will change in order to accommodate the epsilon A term. It becomes V is equal to V naught to 1 plus epsilon A XA. And XA can also be written as a volume as V minus V naught by V naught epsilon A. Let us consider the reaction A giving 4R. So epsilon A is equal to 4 minus 1 divided by 1, which is 3. So far we have seen the type of reactions and how a rate equation can be written. Now all these reactions has to take place in a reactor vessel, isn't it? So there are basically 3 types of reactors. One is a batch reactor, the other is a REACTOR reactor, and the other one is a MFR or otherwise known as continuous stir tank reactor. So if you would see here, the batch reactor and the MFR are more or less look the same, but they are different in the base of the input and the output. So here it means that for a batch reactor, there's not a continuous input nor a continuous output. So it's just allowed to react for a certain period of time. Both of them have agitators to uniformly mix the reactant components. We'll see them in detail, how to derive the design equation. But first, basically, it should start with the material balance. So whatever reactant we put in an element of volume will not be the same amount which comes out as a product. So there will always be a disappearance due to the chemical reaction or accumulation of the reactant inside the element of volume. So the material balance can be written as rate of reactant flow into element of volume is equal to rate of reactant flow out of element of volume plus rate of reactant loss due to chemical reaction within the element of volume plus rate of accumulation of reactant in element of volume. So batch reactor is specifically preferred for research conditions because it can process small amount of materials and for a certain period of time. And besides, the same reactor can be used for different types of materials. So now for Deriving the design equation of a batch reactor, we start with the material balance, which is rate of reactant flow into element of volume is equal to rate of reactant flow out of element of volume plus rate of reactant loss due to chemical reaction within the element of volume is rate of accumulation of reactant in element of volume. So in a short form, it can be put as input is equal to output plus disappearance plus accumulation. So since we can understand from the operation of the batch reactor, during the reaction there is no input or output, these two terms become zero. So it's finally left with rate of loss of reactant A within the reactor due to chemical reaction, which will be equal to minus of rate of accumulation of reactant A within the reactor. So when we write this in terms of disappearance, it becomes minus Ra into B, and accumulation, it becomes GNA by dt. So when we replace in terms of the disappearance and the accumulation into the main equation, it becomes minus RAB is equal to Na naught dxa by dt. So on integrating and rearranging, we get T is equal to Na naught 0 to xa dxa by minus Ra into B. For a constant volume reaction, this equation will become T is equal to Ca naught 0 to xa dxa by minus Ra, which can also be written to be integration between Ca naught to Ca minus of dCA by minus Ra. In terms of variable volume, we have to accommodate the epsilon A terms. T is equal to Na naught 0 to xa dxa by minus Ra to B naught into 1 plus epsilon xa, which can also be written this Na naught and B naught can be clubbed together to be written as Ca naught 0 to xa dxa by minus Ra to 1 plus epsilon xa. So the design of a batch reactor has to be finally represented with the graph. So the y-axis can be 1 by minus Ra versus Xa. So the area for a batch reactor, the area below the curve has to be taken, and that will give T by Na naught. And if 1 by minus Ra is plotted against Xa, the area under the curve will give T by Ca naught. Whereas if it's plotted against 1 by minus R, if it's plotted against concentration, area under the graph will give T. So there are advantages and disadvantages of batch reactor. Advantages is high conversion per unit volume for one pass. Flexibility of the operation is there because you can process different materials in the same reactor. It's easy to do. Whereas the disadvantages are high operating cost. Product quality is more variable than with the continuous operation. See, pass on to the continuous reactors like CSTR, which is otherwise known as CFSTR, which means continuous flow third tank reactor, or it's otherwise known as mixed-flow reactor or a backmix reactor. The next type is a plug flow reactor, which is otherwise known as a tubular reactor. In continuous reactors, we have to make note that we have to use space-time in terms of time, because accurate measurement of the time cannot be considered in for continuous reactors. So space-time is defined as time required to process one reactor volume of heat measured at specific conditions. This got the units of time. And space velocity is the inverse of space-time, which is the number of reactor volume of heat at specific conditions which can be treated in real time. It has got the units of time inverse. So space-time have different representation like tau is equal to 1 by S is equal to Ca naught B by Fa naught is equal to volume by volumetric. So first we'll consider the design of an MF, otherwise known as CSTR or CFSTR. So here the speciality of MFR is that the conditions inside the reactor will be the conditions outside the reactor. So starting from the material balance, input is equal to output plus disappearance by reaction plus accumulation. The accumulation term is considered to be 0 because we assume a steady state. So in that case, the input becomes Fa naught into 1 minus Xa 0. Since Xa 0 is 0, becomes Fa naught. And output is Fa, which can be written to be Fa naught into 1 minus Xa. And disappearance of A by reaction will be minus Ra into B. So substituting all these terms in the main equation, we'll be left with Fa naught XA is equal to minus Ra into V. So which can be rearranged to be V by Fa naught is equal to tau by Ca naught is equal to Xa by minus Ra. In terms of the different forms of tau, it becomes tau is equal to 1 by S, V by V naught is equal to V Ca naught by Fa naught is equal to Ca naught Xa by minus Ra. So this can also be written in terms of a constant volume reactions like V by Fa naught is equal to Xa by minus Ra is equal to Ca naught minus Ca divided by Ca naught into minus Ra, and it has to be represented in terms of graph. Just like previous ones, the inverse of rate versus concentration and the conversion. Now, a special notice has to be given to the MFR or the otherwise known CSTR is that area above and below the curve has to be taken. Whereas it's not so for Plateau reactor or batch reactor. So when it is plotted against conversion, rate versus conversion, the area above and below will give V by Fa naught is equal to tau by Ca naught. Plotted against concentration, it gives tau is equal to V Ca naught by Fa naught. The equation for a constant volume first order reaction is K tau is equal to Xa by 1 minus Xa is equal to Ca naught minus Ca by Ca. And for any epsilon A first order reaction, it becomes K tau is equal to Xa into 1 plus epsilon Xa divided by 1 minus Xa. The second order reaction for constant volume, it becomes K tau is equal to Ca naught minus Ca by Ca square. So the advantages of CSTR, otherwise known as MFR, is that it's a continuous operation, because good temperature control, easily adapts to two-phase runs, simplicity of construction, and low operating costs. Whereas the disadvantages are bypassing channeling. Next reactor which we're going to consider is the PFR, otherwise known as a tubular reactor, based on the nature of the, or you can say the shape of the reactor. So starting with the material balance, we have input is equal to output plus disappearance by reaction plus accumulation. So as similar for MFR, since it's continuous reactors and we assume steady state, accumulation is taken to be 0. So input is equal to, we will just consider a small element of volume, then we integrate it to the entire reactor. Input is equal to Fa and output is equal to Fa plus GFA, and disappearance is equal to minus Ra into dV. So when we substitute all these terms in the main equation, we get Fa is equal to Fa plus GFA plus minus Ra into dV. And this can further be expanded as dFA is equal to d into Fa naught 1 minus Xa is equal to minus Fa naught dXA. Fa naught dXA will become equal to minus Ra into dV, which when we integrate between the limits 0 to v dV by Fa naught and this term is 0 to Xa, dXA by minus Ra becomes v by Fa naught is equal to tau by Ca naught is equal to 0 to Xa dXA by minus Ra, and tau is equal to v by V naught is equal to V Ca naught by Fa naught is equal to Ca naught 0 to Xa dXA by minus Ra. And for constant density systems, this becomes Xa minus 1 minus Ca by Ca naught. And you can substitute this term, final equation, and becomes V by Fa naught is equal to tau by Ca naught is equal to 0 to Xa dXA by minus Ra. Or that is also equal to minus 1 by Ca naught integration Ca naught to Ca by minus Ra. So for a zero order homogeneous reaction, constant epsilon A becomes K tau is equal to K Ca naught B by Fa naught is equal to Ca naught Xa. Whereas for first order irreversible reaction, K tau is equal to minus 1 plus epsilon A ln of 1 minus Xa is minus epsilon A Xa. For first order reversible reaction, it becomes K1 tau is equal to M plus R Xe divided by M plus R to 1 minus 1 plus epsilon Xe ln of 1 minus Xa by Xe minus epsilon Xa. So this also has to be represented graphically. Graph between 1 by minus Ra versus Xa has to be plotted. The area below the curve will give V by Fa naught is equal to tau by Ca naught, and the graph is plotted between 1 by minus Ra versus Ca. The area below the curve will give tau. So the advantages of Plateau reactors: high conversion per unit volume, 1 pass, low operating cost, continuous operation, good heat transfer. Disadvantages is shutdown and cleaning may be expensive, undesired thermal gradients. So many reactors can be connected in series or parallel. So there are a set of general rules which can be applied. For a reaction whose rate concentration curve rises monotonically, reactors should be connected in series. They should be ordered so as to keep the concentration of the reactant as high as possible. The rate concentration curve is concave. As low as possible, the curve is convex. For reaction where the rate concentration curve passes through a maximum or minimum, the arrangement of units depends on the actual shape of curve, conversion level desired, and the units available. Basically, no simple rules can be followed. It's better to draw a rate versus concentration curve, find the best arrangement. Apart from the simple or simple reaction which I have seen till now, there are multiple reactions also which require more than one stoichiometric equation and then one range equation. So the design factors for the reactor become size of the reactor and the product distribution, because one of them will be an undesired product and the other is a desired product. So examples of multiple reactions are series reaction, parallel reaction, and series parallel reaction. So series reactions are those where reactant gives rise to intermediate, which most often is the desired product, which finally decomposes to the product, which might not be a desired product. Could be an undesired product. Parallel reaction is those where A will parallelly give R and give parallelly given other product S. The R can be a desired product and S can be an undesired product. Series parallel reactions are those which are a combination of a series and a parallel reaction. A plus B will give R and R plus B will give S. So when we consider a parallel reaction, as I already mentioned, R is the desired product and S is an unwanted product. So when we write the individual range equations, R of R is equal to dCr by dt is equal to K1 CH to the power of K1. R of S is equal to dCs by dt is equal to K2 CH to the power of K2. And R of R is equal, R of R by R of S is equal to dCr by dCs is equal to K2 C1 CH to the power of A1 minus A2. So this A1 and A2 can be represented to be N1 and N2. So any representation where A1 or N1 is order of the desired product and N2 or A2 is order of the undesired product. So then we'll have to have the concentration of the reactant to be as high as possible. If it's in the gas phase, the reaction should be run without inerts and at high pressure. If it's in the liquid phase, the reaction should be run without diluents. A batch of BFR should be used since CH starts at a high value and drops over the course of the reaction. If A1 or N1 is less than N2 or A2, concentration of the reactant has to be kept to be as low as possible. If it's in a gas phase, the reaction should be run with inerts and at low pressure. If it's a liquid phase, the reaction should be run without diluents. A CSTR recycled reactor should be used. If for the order of the desired reaction A1 or N1 equal to order of the undesired reaction A1 or A2 or N2, then we can change the temperature or we can use a catalyst. If we consider a series reaction, we can consider two types of arrangement. Say for example, this is a beaker having the reactants and it's irradiated with light. So when we plot the concentration, this is the progress of time since light was turned on, A will slowly disappear and R will slowly start forming and start decreasing to give way to S which is forming. So in this case, where a certain light source is given to a large amount of reactant, we have the formation of the desired product R. But when we consider this type of arrangement, where we take a small amount of reactant and then we're irradiating with the same amount of light, what happens is R will immediately become S. So that is why we see in the x-axis the level of R. which means that there is no formation of R. A will slowly decrease, R will form, R will immediately become S. So we want only the desired product, which is R. So we, as an engineer, will consider the first type of arrangement for the production of desired product. When we consider a series parallel reaction, these two type of behavior can be expected, that A is added to bigger B, bigger which contains B. If we consider the series parallel reaction, A plus B giving R and R plus B giving S, what happens is, when we plot a graph between amount of B and moles of A added differentially, then what happens is A will slowly start decreasing and B will also slowly start decreasing, and then S will start forming where there is no formation of R, which is the desired product. But when we consider another arrangement, like these two arrangements will have the same behavior. The B is slowly added to A and B added together. So in this case, A will slowly start decreasing, give rise to the formation of R, which will increase and then decrease, which will allow for the formation of S. So in this arrangement, we can add the formation of the desired product, which is R. So this arrangement is most preferred. So the references for this lecture was taken from Chemical Reaction Engineering, 11th Street, and Chemical Reaction Engineering, K. Gavan. Thanks a lot for your patience.